Okay, great. Okay, great. Thanks for having me. That's Charles Martin. I run a boutique consulting firm here in San Francisco, California. I've been doing this for over a decade, where we build machine learning and AI products for companies. And I'm going to talk to you today about an open source tool we've developed called WeightWatcher, which is a diagnostic tool for analyzing deep neural networks. Let's see if I go forward. Now, my background, I did my PhD at University of Chicago in theoretical chemical physics, quantum chemistry type stuff. And then I was an NSF fellow in theoretical chemistry and physics at UIOC, where I actually worked in a group studying the statistical mechanics of neural networks. So I had been exposed to these ideas way back in the 90s. And there is a very rich history of applying statistical mechanics to understanding deep learning. And all the techniques I'm going to talk about today are really based in the theory of statistical mechanics. I won't go through all of that. We can talk about that another time, but that's what we're talking about: statistical mechanics and complex systems, and using it to build a diagnostic tool to analyze deep learning. Now, I've built this tool because I do a lot of work in industry and I see a lot of problems in industry. A classic problem would be somebody deploys a model to production and then it breaks. And you don't realize that it broke for 3 months because there's no way to monitor it. These are very complex things. And this is essentially a type of monitoring tool, which allows you to see what happens in your models and to analyze them layer by layer. And I don't think there's any other tool available, or any theory really, that can let you analyze neural networks layer by layer to understand how they're performing. So I've worked at a lot of companies. So you can see going from BlackRock, Google, eBay, private equity, things like this. A lot of these ideas, again, come from statistical physics, and also from my work at BlackRock was a quant, where we used random matrix theory to understand how to model the covariance matrices we would deal with. This is work that's done in joint with an old friend of mine, Michael Mahoney, who is an expert in randomized linear algebra, and was also a theoretical chemist many, many, many years ago prior to doing this. And we had talked about this. We've been talking about this almost for 10 years, so we're finally getting some traction on the problem. He's at UC Berkeley, so he's been a great help, and I work with him and occasionally with his students. But for the most part, this is work that's been done totally independently. I don't have any formal association with UC Berkeley. We just do it because it's interesting. So what are the motivations here? Well, a few years ago, there was a paper that came out that was trying to argue that understanding deep learning requires rethinking how generalization works. And this, I think, in 2016, 2017, and we wrote a paper saying understanding deep learning requires remembering how generalization works, because there's a whole theory of generalization from the perspective of statistical mechanics, which is very, very different than statistical learning theory. And what we're presenting here is really a phenomenology using ideas from random matrix theory and motivated by the statistical mechanics of generalization and strongly correlated systems. But this is pretty nerdy stuff, very technical. I don't have time to go into all of it. So what I'm really going to do is just show you how the tool works, how you can use it when you're looking at deep neural networks, and just give you a kind of an overview of what the basic ideas are. So this is an excerpt from our paper in Nature, which we published last year. The idea of WeightWatcher is that you take a model, some pre-trained model, VGG19, GPT-3, some model you have, and the tool will iterate over every single weight matrix, and it does spectral analysis. In other words, it computes a histogram of the eigenvalues, using singular value decomposition. It gets the eigenvalues of the correlations, and then it makes some plots. And what we find is when a model starts off, it's initialized randomly. And if you apply random matrix theory, you sort of get this red curve, which is the Marchenko-Pasteur line from random matrix theory. And this purple is the histogram of the initial weight matrix. And as the system undergoes training and begins to learn, you see that this spikes large eigenvalues start pulling out from the edge of the Marchenko-Pasteur distribution. And this is known from random matrix theory that when you have something like a large rank 1 perturbation, you'll see these spikes will appear. And then when you start getting enough spikes, the random matrix bulk region disappears, and you get something which is heavy-tailed and actually fits a power law or a truncated power law quite well. And so the whole point here is that when a system is learning information, whether it's a neural network or even a simple model like latent semantic analysis, for example, it will begin to, the information gets concentrated in the eigenvectors corresponding to the large eigenvalues of the weight matrix. And as you learn more and more information, these eigenvalues start becoming randomly distributed on a log scale. You pick up information on different levels of granularity and you form a power law. And this turns out not only to be, we see this empirically, but it's also quantitatively predictive. And the tool, what the tool does is it takes your models and does this analysis for you. So the tool is very simple to use. If you're a Python programmer, you just say pip install WeightWatcher, import WeightWatcher's WW, watcher equals WW WeightWatcher, model equals, you specify your model. If you say watcher.describe, you'll get a data frame, which gives you basically a description of how we're going to label the layers. So you can understand what the IDs are, what their sizes are, what their names are, and just to make sure the tool is working. If you say watcher.analyze, it will go through and compute various metrics. If you say plot equals true, it will add plots, and you get a data frame of results. And these results are quality metrics, which can be applied layer by layer. They're layer by layer quality metrics, which tell you whether your model is performing well or not. And then you can also get like a summary from it, like a layer averages. You average over all the layers. We have a GitHub page, github.com, calculated content WeightWatcher. You can go there, download the tool, read our papers, get some very, very basic usage of how the tool works. The idea is that you can analyze pre-trained PyTorch and Keras models and some ONNX support. I'm not a fan of ONNX, but we try to support it. It allows you to inspect models that are difficult to train. You can gauge improvements in model performance. In other words, you can take two models that you have, vary the hyperparameters, and the tool will give you some estimate of which model will perform better. It can predict the test accuracy. So given a series of models, it will actually predict the test accuracy for you. So you can imagine if you're making some model that is trying to predict market behavior in some way, it's useful because you don't want to peek at the market data. Otherwise, you can overfit. And it can also detect problems like when compressing or fine-tuning your models. So I encourage you, if you're doing anything, to pip install WeightWatcher and give the tool a try. Give me some feedback and let me know how it works. Here's a list of papers that we published. We have a large paper in JMLR, which sort of goes through the phenomenology based on random matrix theory. Another notable paper from Nature Communications, where we do a meta-analysis of over 100 models, and we show why the WeightWatcher Alpha-Hat metric works. We have some other papers in press today that we're submitting to various conferences. One which is an analysis of why the Alpha-Hat metric works, looking for Simpson's paradoxes. Others, we have one where we can train a transformer to state-of-the-art accuracy, and we can monitor the model quality epoch by epoch using our metrics. There are also a number of results which are unpublished and experimental. And when I go through the talk, I'll try to clarify what's been published in very high quality journals, what we've discussed in conferences, what is in press today, and what is just sort of ideas we have. But this is the basic idea. Take any layer of a weight matrix. You compute its eigenvalues, or the singular value decomposition. You take the square that gives you the eigenvalues, plot it on a log plot, and you'll get a plot that looks, the WeightWatcher will produce a plot that looks like this. It will then attempt to fit the tail of the distribution to a power law or a truncated power law. To do that, you have to specify what is the maximum eigenvalue, the scale, which is this orange line, which it finds for you. And then you have to specify the start of the tail, which it tries to find through brute force. When it does a good fit, it will find the start of the tail. And here you'll get this red line, which is where the tail starts. When it does a bad fit, maybe you'll get something like this purple line. And so when you get good fits, that tells you that your model is working well. It turns out that in almost all cases we've looked at with very, very high performing state-of-the-art models, the layers tend to fit a power law or a truncated power law very, very well. And so that basically, you're looking for this straight line. We don't use a straight line fit. We use a statistical estimator. But the idea is you want to try to fit this power law and get an idea of how well the fit works. The better it fits a power law, the better your model seems to work. And we actually have data to show this. We're not doing anything particularly complicated. just to give you an idea, we're simply taking the weight matrix, we're looping over the layers. We actually use singular value decomposition. Basically, we form this correlation matrix and we get the eigenvalues. And the key here is that we're looking at the correlations. We're not looking at W. We're not looking at W element-wise. We're looking at the correlations. And it's the correlations which tend to show this heavy-tailed behavior. When you run the tool, you'll get a data frame. You say watch or analyze. You'll get a data frame. Here's like the layer ID, the way we pick it. Sometimes it skips layers it doesn't understand. It will tell you the shape. These are rectangular layers. It will give you this alpha metric, which is the exponent of the power law, and a variety of other quality metrics, which you can read about on the GitHub page or just ask me and I'll explain to you how they work. But this is essentially what you get. You give it a model, you get back a data frame. So the key idea here is that the phenomenology tells us that the more heavy-tailed the correlations are, the better your model should perform. Now we can derive these, we can have a theory which is based in statistical mechanics. It's a matrix generalization of an old model called the student-teacher model from the statistical mechanics of generalization. And I can go through that at some point and describe, we can derive all of this using fairly, semi-rigorous techniques. But the key idea is the heavy-tailedness. This is the core idea, that when you look at the weight matrix itself, the weight matrix itself should have no unusually large elements. And you can check this just simply by permuting it and commuting its spectral density. So if you permute, so there's an option in the tool called Randomize, and it will produce plots like this for you. This is right out of WeightWatcher. It will take the W matrix, it will randomize it, and it will compute the spectral density, the eigenvalues of the randomized W. And if W is behaving well, you'll see that it forms sort of this semicircle on this is a log scale. This is log, not log, but log. But you'll get this kind of plot that sort of looks like a semicircle with the maximum eigenvalue at the edge. And this tells you that W has no unusually large elements. But X, which is the correlation matrix, can have many, many large eigenvalues. And the reason this is relevant is because if you look at other theories in theories of learning, which are based on statistical learning theory, pack balance theory, things like this, they're trying to bound W. And our point is that that's conceptually kind of the wrong thing to do. Because yeah, it's true, you should bound W because you don't want W to have large elements. In other words, you regularize, you add L2 regularization. From a statistical physics perspective, you're trying to control the temperature. W is like a temperature measure. So you're trying to keep the temperature down. But that doesn't mean that W's eigenvalues would not be large. And I think this is where people sometimes get confused and they conflate the idea of regularizing W and bounding it with saying that it has no large eigenvalues. And in fact, what you want is you want these large eigenvalues and you want them distributed in a way that you get this nice tail, because the information in the network concentrates in the tail. And the more regular this is, it appears to be that systems generalize better when it captures correlations on different levels, on different scales in sort of a uniform way. So WeightWatcher will actually analyze these spectral densities for you and give you different quality metrics. So here's an example of looking at a model that was released a few years ago by OpenAI called GPT-2. And we discussed this in our Nature paper. We look at GPT-2 and we're going to compare it to GPT-3. And GPT-2 is a model which was trained on sort of insufficient data. And GPT is a model that was trained on insufficient data because OpenAI didn't want to release a model that would let you generate fake text. And then later they said, well, we're going to let you release them. We're going to actually start giving you models that actually can generate fake text, but we're going to charge you for them. So GPT and GPT-2 are trained on the exact same model, exact same architecture, but the data is better in GPT-2. So they purposely broke GPT. And what you find is that you can see the fact that GPT is broken by looking at the weight matrices. Again, we don't look at the data. We don't have the data. We didn't train GPT. We're just looking at the open source tool, the open source model that was released to the public. In GPT, you see that I picked just a random layer 146. You see that it fits a power law, but the fit's a little squirrely, and the alpha is 4.12. With GPT-2, you see that it fits a power law, but it's a better line and the alpha is smaller. And again, the idea here is that we're taking the ESD, we're fitting the eigenvalues to a power law. So the rho of lambda is, we're fitting the tail to a power law. And generally what we find is the alpha, the exponent, lies within a range of 2 to 6, which is what we call the sort of fat-tailed heavy, this universality class, which are fat-tailed or moderately heavy-tailed random matrices. And you generally get a good quality of fit. And what we know is that well-trained layers are heavy-tailed and well-shaped. The tool will go into more detail of how you do these fits and how you select exponent. I won't go into that here for time, but basically the tool gives you all these different plots to try to help you understand whether you got a good fit or not. If you look at GPT versus GPT-2, you'll see that generally speaking, when you have better data, the alphas are smaller. We can look at all the layers. So let's look at all the layers. These are all the layers and the alpha, that exponent for GPT versus GPT-2. GPT is in blue, GPT-2 is in red. And you'll see that on average, the exponents are a little smaller. This is the peak. So the peak is around 3.5 in GPT-2, where in GPT, the deficient model, the peak is a little larger at 4. More importantly, you see you get a bunch of large outliers here for GPT-T, the bad model. These are bad fits. These are cases where the fit did not work correctly or the layers were nearly random. So the original GPT model, having poor data, is trained poorly on purpose, and you can see this using the tool. So you can use the WeightWatcher as a diagnostic tool to help you understand whether you have enough data in your model or whether you have severely too little data. This is one of the ideas we think you can use with this theory. Now, there's a certain kind of universality that we've seen. We've looked at this point, thousands, tens of thousands of matrices, linear convolutional maps, and generally we find that almost everywhere we look at the exponents. This is a histogram of the exponents, looking at, this case, 500 matrices over 50 architectures. We've extended this to tens of thousands of layers. They all pretty much have an exponent between 2 and 6. There are some outliers which are a little less than 2, some they're more, but for the most part, 80 to 90% of your exponents are going to lie in this range. And so this is sort of our experimental result, which allows us to build a phenomenology. So, we approach the theory of learning as a sort of like a physicist in the 1920s, prior to World War II. Things are phenomenological. We look at data, we look at experimental data across many, many models, then we build a phenomenology, and from there we build a semi-empirical theory. So we've done a lot of this sort of meta-analysis. From this meta-analysis, we have this sort of phenomenological theory. So we take random matrix theory, and we note that when you begin training a model, the weight matrices are random. You initialize them with random matrices, usually some sort of clipped random matrix. And if you apply random matrix theory, you try to fit the density to a random matrix, it gets a perfect fit. As you begin training, this is an example of either as you begin training, or in this case, we took a model and we just decreased the batch size. We forced on the regularization. So as you train, or as you increase the regularization, the onset of learning shows the appearance of these large eigenvalues, which are called spikes. In small order models, we see these spikes appear, and these spikes, we believe, contain the information that helps the model generalize. These are the generalizing components. And as you train more and more, and as you increase the regularization, you see more and more spikes until eventually this heavy-tailed distribution falls away. So we believe that the training induces a breakdown of the Gaussian random structure and an onset of a new type of heavy-tailed self-regularization. And in our paper, we go through what's known sort of from the finance and physics literature about what we know about heavy-tailed random matrices, and we build a phenomenology around that. This is just sort of showing, here's what, if you have a random matrix, when you change the aspect ratio, you get different shapes. So this is called this is Marchico-Pasteur theory. Random matrix theory tells you that depending on the shape, the width versus the height, you can predict the shape of the spectral density at different aspect ratios. And critically, you get a shape which is well defined, and you get these very, very crisp edges. And the key is that when you look at real matrices and you zoom in on any of them, you find out that whilst you can get a random matrix fit, you can always fit anything, right? The fit always has these large, the crisp edge is gone, and typically the fit is not very good. And so this is what we see. And we see this starting with AlexNet, any model from AlexNet on, we see this behavior. And this is right out of finance. It's right out of the finance literature. This is a paper by, I think, Bouchard, where they said, let's look at the covariance matrices of some market data, and we see the exact same behavior. You may find that the market data shows this heavy-tailed behavior. Here's a fit the random matrix theory, this green line. Here's real data. So a lot of these ideas come directly out of trying to model market data and understanding why they fit power laws and what you can do with them. So this is our phenomenology. If you look at our paper, we sort of describe these different phases of training. And the idea being when you're well behaved, you're somewhere in a bulk decay or heavy-tailed region, you want to avoid layers that sort of look bleeding out or bulk plus spikes because they're not trained enough. And you want to avoid layers that are too heavy-tailed or have a singularity because they're overfit or exhibit some kind of rank collapse. And again, we go through all this in this very long paper in JMLR. This is the basic idea. You want to look at your layers and try to understand these are undertrained, these are overfit, these are underfit. And the idea of the theory is to let you detect this in a model and to do it layer by layer. The paper goes through these various universality classes. So the idea is we took a phenomenology from random matrix theory. We use a theory where we're using a theory where we're characterizing W as random. But we're really saying, look, it's not that W is random, it's that the correlations are random. But we don't have a good theory of correlation. So we use sort of a theory for just general random matrices and try to fit the correlation matrices into these various buckets. And then we observe the buckets in practice. And the whole point of the tool is it will try to tell you where you are. Things you can do, this is a critical idea. If you measure the average power law exponent, the average alpha, just take a layer average. It turns out that this is predictive of your generalization capacity. So not only do these models fit heavy tails, but the amount of heavy-tailedness, how heavy-tailed it all, how heavy-tailed the layer is, however you measure it, using power laws, using the spectral norm, using truncated power law, depending on the situation, the exponent, the amount of heavy-tailedness is correlated with the generalization. So in most models that are not, we're trying to look at sort of a coarse grain level, power law is good enough. And it turns out that here's an example of some models we took from a contest, and this is something that we're submitting now. Here are various models have different numbers of layers, and the model in blue has, I think, something like 13 layers. The 2 is just an arbitrary label. But models with more layers tend to have higher test accuracies, and models with less layers have less test accuracies. And you see that if you plot the average alpha, which is just the layer average versus the test accuracy, the more accurate the model is, the better of a fit you get. And it's quite predictive. So alpha itself is predictive generalization at a fixed depth. You fix the architecture and you're just changing the amount of regularization. You're changing the hyperparameters, the batch size, the amount of momentum, the step size of the solver, anything that affects the amount of dropout. When you change the regularization, you can show quantitatively that the power law exponent is correlated with the test accuracy. Again, we didn't train these models. Somebody else gave them to them. We don't have access to, we don't actually measure the test data ourselves. We're just looking at the reported test accuracy and looking at alpha. It turns out if you look at other metrics like the log spectral norm, you see sort of weird behavior, this sort of Simpson's paradox behavior, which don't work. And so we sort of argue that there are metrics, things that look at the scale sort of screw you up. But so I won't go into too much detail other than to say that most people in the field are looking at the scale of the weight matrix because they're trying to find a bound. We're not trying to look at the bound. We're trying to look at average case behavior. And with average case behavior, you don't use statistical learning theory, you use statistical mechanics. And so we have cases where we really can show that if you try to apply bounding theorems, you get sort of funny results. When you apply our theory, you get very consistent results. Other things you can do, we have a metric called Alpha-Hat. Alpha-Hat is a weighted average of alpha, where you weight it by the spectral norm, which is the scale or the size of the matrix. Because it turns out that the alpha fits don't so much depend on the aspect ratio, so we have to adjust the weighted average by the scale of the layer. And when you do that, not only do you get good fits, but you also can get good fits across different depths. So when you can predict accuracies across variations in hyperparameters and depth. Recall that I said that the alpha metric lets you model hyperparameter changes in regularization. Alpha-Hat lets you measure changes in regularization and depth or architecture. So here are some examples of that where and this is published in Nature, where we look at various models like BGG, and we look at the average Alpha-Hat, and we show that Alpha-Hat is actually well correlated with the reported test accuracy. Again, we don't have access to the training or test data, but we can predict trends in the generalization. This works for hundreds of different models, looking at cross-validate, computer vision, natural language processing models. It's very consistent. We've looked at models like ResNet. If you look at a small number of ResNet models, you get a pretty good fit. RMSE of 66, R-squared 0.95. If you look at all the ResNet models that have ever been created, we've actually gone all the way up to ResNet 1000 at some point. You get a good fit. Obviously, the R-squared is a little smaller, at 0.86. The RMSE is a little larger, but you still get a pretty good fit. So again, the idea of heavy-tailedness is correlated with quality. And this is predictive. It's predictive of quality of models. And so you can use the theory to analyze different kinds of pre-trained models you're training. You can look at the layers, you can evaluate their quality, and these quality metrics allow you to detect problems or to predict behavior simply by looking at the weight matrices themselves. I'm almost done here, so I'm just going to see if I can find anything else that might be interesting. So other things you can do, you can look at the alpha versus the depth or the layer. And so we can see the correlation flows. You can use the theory to understand how to design better architectures. So here's an example where we look at 3 models, VGG, ResNet, and DenseNet, applied to the same, trying to predict the ImageNet data, the same data sets. The VGG architecture, if you look at the layer alpha versus, the layer ID. So the data is sort of here and the labels are here. The data, think about these layers are closer to the data. These layers are closer to the model, the labels. In VGG, the alphas start very small. We think the early layers maybe overfit a little bit. As you move through the model, you get less and less correlation is being captured in the layers. And then you have these 3 little layers, these 3 little fully connected layers at the end of VGG. So these are convolutional layers. These are fully connected. And so you have these convolutional layers, convolutional max pool, convolutional max pool, convolutional max pool, fully connected. And the fully connected layers then recapture the correlation, which was lost at the end of the convolutional maps. In ResNet, when you add residual connections, you find that you get a much smoother correlation flow. We're looking at the ResNet 152. All the layers are around 2. There are some outliers. And basically, the layer correlations stay pretty well concentrated till you get to the end. And at the end, they sort of near the labels, they kind of blow up, or we get some outliers, or maybe they're just not a great fit. But you can see how the correlation flows much, much smoother throughout the ResNet layers. In DenseNet's an example where they just have residual connections everywhere, like as many residual connections as you can put in. And when you do that, you see that the correlations are all over the map. So there's no smooth correlation flow throughout the architecture, but instead the alphas are just basically random with some small trend going from some small trend rising up. So this is pretty consistent with the theory and with things that other models of correlation flow. We're not the only ones who can do this, but I think we're the only ones who can do it in a way which is independent of the actual data. We just look at the model. So you can actually see how correlation is flowing throughout your models, and you can use this as a diagnostic tool to figure out how to design better weight matrices, for design better layers by looking at design better neural network architectures by looking at the correlation flow. The only thing I want to talk last about is this idea of correlation traps. I'll just say very quickly. We started off at the talk by saying that the amount of heavy-tailedness matters. So if you say watch or analyze plot equals true, and you say randomize equals true, it will attempt to characterize the weight matrix by permuting it and looking for unusually large elements of W. These are examples of what we think mean overfitting, or what we would say where the regularizer fails. And you can see you get these sort of unusually large elements of W, almost like rank 1 perturbation, just unusually large elements which should not be there. And according to pack bounds theory, they should not be there either. And we have a method which we call SVD smoothing, a sharpness, excuse me, where you could actually use WeightWatcher to clip your model to remove these large elements using random matrix theory. So you can remove them and then retrain again. So it's sort of like a type of regularizer where you clip off large, it's type of clipping algorithm. It's very common that people might clip W elements, but instead of just randomly clipping with a threshold, we improve the clipping by using random matrix theory to clip off these elements and then return your model so that you see that your model's layers should not look like this right-hand side. This is bad because these large unusually elements of W tend to trap the correlations. When they're clipped out, you get a nice smoother behavior. So this is the kind of behavior you're looking at. And again, we have a number of transforms in the tool, which allows you to clip this and to then see that you've actually performed the right, that you're training well and that you're not getting this sort of anomalous behavior. So that's about a half hour. I'll stop there. There's a ton of other stuff that we do with the tool, but I sort of just lay out the basics and where the ideas come from. Again, this whole idea of the layer being heavy-tailed, this comes right out of complex systems theory, that the idea that, when you're in a system is near a phase transition, that you see heavy-tailed behavior and that you see correlations that appear on every scale. And it's sort of motivated by the same idea that in these weight matrices, we expect them to be strongly correlated. When they learn, they're strongly correlated. So you expect to see correlations appearing on every scale, sort of uniformly on every scale. And this is why you see power law or truncated power laws in the correlation matrices. So I'll stop there and open the floor to questions.